Okay.
I mean, I'll be there, so we can do those after.
Highlighted number 1.
Oh, hold up. Hold up. Oh,
No eating in the lab, good thing this is early.
Based upon this equation, hydrogen peroxide plus 3 iodines plus 2 H plus, which means it's in acidic solution. That's what that means. Makes I3 plus 2H2. All right. So that's the overall equation. But the question is, what's the rate law? We can't determine the rate law from that. What we need is more information. And that's given in the rest of the problem. First order in H2O2. So we have a rate constant. Then we have concentration of H2O2 to the what power? First power. So I don't write anything up there. Well, it could, but just to be thorough. And then second order in the iodide ion. Second order. And then it says 0 order in hydrogen ions. Okay. So what does that mean as a practical matter? What's that? That's equal to 1, isn't it? Right. So that's the rate law. That's why E is the answer instead of A.
So E and A, they're not like the same.
Well, I guess you could say technically, but we're thinking mathematically, anything to the 0 order is 1. So we know that the rate law should have all 3 terms in it. But since this term is missing, we can assume that it's 0 order. And its rate is dependent only upon K. All right, number 2. Have you looked at the others? I mean, have you looked at the whole thing? All of them? No. That's okay. I picked out some that I thought were the most reasonable ones. Some of them in there were really hard to make sense of.
well, thank you.
Yeah, so we're not gonna beat our heads against the wall over those. These are basic things. So if the rate law is this one, equals K times A to the what? It's a 212. 2, 1, 2. What's the question? What's the overall order of this rate law? We know the order with respect to A is 2. The second order. First order would be second order C. So what's the overall?
Ah,
Yeah. Right, 2 plus 2 plus 1.
Yeah, okay, yeah,
Just add them together. Mhm.
I like that.
Steve, pull it up. Give us some of them.
There'll probably be one like that.
Just one? You go in a few.
Number 4. If the reaction 2HI to hydrogen iodide yields what? H2 and I2. Okay, is second is second order. Yeah, second order with respect to only one reactant. Right, if it's second order, then we could write the rate law equals K times HI2. Question is, which plot will give a linear?
Inverse.
Yes, inverse. So we'll do
Do
time.
inverses always give you linear?
If it's second order.
Okay.
Yeah, for second order, the inverse will give you second order. I mean, it'll give you straight line versus time. Okay. That was simple enough. What would, if it were first order, which one would it be?
C.
I don't know.
Natural log. Zero order, the raw data will give you straight line. Yeah. First order is natural log, second order is inverse.
Zero order is the
Would be the one you answered, yes. That would be zero order. And D would be first order.
What date?
Yeah. So if I put a question like that up there and I changed second order to first order,
What did you say first was? I mean.
natural
A-
log,
No, what order is that? There's natural? The order of A.
oh, the order of A?
Yeah. What one did that?
Nothing.
Seven? Okay.
No, because that's the common log. You need the natural log. A is in there to confuse.
Okay.
The only ones that are valid are B, C, and D. And it depends on whether we're talking about zero order, first order, or second order. Number 5, that one's starting to get weak. Let's try another one.
We're doing that in our lab today, ain't we? The second order, first order,
Yeah,
inverse stuff.
we're doing decolorization of blue dye with bleach.
Yeah, and
Yeah.
then we have to graph them, and each of those graphs are gonna be different. Or like,
Yeah, you have to find out, first of all, which order is the blue dye. And that's from plotting the data. Enzymes, which is incorrect about enzymes. They're usually proteins that catalyze specific biological reactions. Now that's spot on. That's what they are. They're usually proteins. They're not all proteins, but the vast majority are proteins. Some of them are actually RNA. Ribonucleic acid. Okay. And they catalyze specific reactions. They usually only catalyze one direction, with some exceptions. Some nasty ones go both ways. B, they're equal to inorganic catalyst in efficiency. No, they're much, much more efficient than inorganic catalysts. Way, way, way more efficient.
Heard it.
B is the false one. Several thousand are known. Yes, the molecules they react with are called substrates. That's true also. Let's see, we're gonna skip that one. How about 8? Remember our discussion of free radicals? I can't find a good marker. I don't want to use these guys right here because they're hard to erase. I guess I'll have to. A free radical is a chemical species that possesses what? Unpaired electrons. Right? A free radical can be anything. It can be an element. It can be an ion. It can be a molecule. As long as there's an unpaired electron, it's a free radical. And free radicals are blamed for cell damage. Right? If we had a perfect biological system that would scavenge free radicals whenever they're created in our body, then we'd live a lot longer. And that's where polyunsaturated fatty acids in our diet are good, because they're really good at scavenging free radicals. Okay, 9. the rate expression for a particular reaction is rate equals K, A, and B is the second order, isn't it? Yeah. The initial concentration of B is increased from 0.1 molar to 0.4 molar. 0.4 molar. So the rate calculated at this value compared to the rate calculated at that value for B, and A doesn't change. So what's the initial rate increase? Well, how many times, what's the factor, the multiplying factor from this one to this one?
4.
It's times 4. So the rate's going to be times 4 squared, or times 16. The rate's going to increase 16 times. Okay. Number 10. Use elbow grease. All right. For which order reaction is the half-life of the reaction proportional to 1 over K? All right. So let's get our half-lives. T1 half equals, and this is 0 order. This will be first order. This will be second order. And so T1 half for 0 order is, I use my cheat sheet, A over 2K. Okay. T1 half for first order, I remember this one, 0.693 over K. Yep. And T1 half for second order equals 1 over A0 times K. Yeah. Okay. So which one's proportional to 1 over K? This one, right? 1 over K. 1 over K. 1 over K. They're all proportional to 1 over K. Surprise, surprise.
Is there a difference in number 11?
No.
That's a duplicate. Did I mark it out?
Yeah, it's on. I mean, it's on here, but
Because there were several duplicates in here. Yeah. Well, I just made a comment. I don't know how that duplicate got in there, but it's there. All right, let's skip down to 13. Looks like we're going to get a question about mechanisms here. Which type of collision is most likely to be the rate determining step in a proposed mechanism? All right, so what we have to assume for this one is that each one of these possibilities, unimolecular, bimolecular, termolecular, there's no such thing as non-molecular. I just throw that in there for fun. So we've got uni, bi, and ter, molecular. You remember how they're characterized. So for a proposed mechanism, the step that's unimolecular just has A going that way. The bimolecular is either 2 A's or A and B. And a termolecular is an A and a B and a C. Or 3 A's or 3 B's. There are 3 that have to come together with the right energy and the right orientation. So if all 3 of these are I'm interpreting the question. If all three of these are in the mechanism, which one would be the rate determining step? The most unlikely one. Termolecular. It's going to be the slowest.
Yeah, you told
And then A plus B is the bi one,
It's the bi.
and then A is the U.
Unimolecular. Yep. And you're not likely to see very many reaction mechanisms that use the termolecular because it's so improbable. We only use that one when there's no other choice. Or when we're just, I don't know. I guess if you do this for a living, you could have fun with termoleculars. Yes, it'd be kind of odd to have fun with that stuff. Okay, 14. The reaction, let's see, 2 hydrogen peroxides yields 2 waters plus oxygen. Has the following mechanism. All right. H2O2 plus I minus yields what? H2O and IO. H2O plus IO minus. And then H2O2. I guess this is the first one and that's the second one. We add this intermediate, IO minus, and that yields water plus oxygen plus iodine. All right, so this is step 1, this is step 2. All right, what's the question? The catalyst in this reaction is what? Well, look at the overall reaction. What down here is not up there? Okay, that's one thing. That's not up there either. Right, so which one of those is the catalyst? The catalyst is the one that goes in the front end, comes out the back end unchanged. Yeah, I. This would be an intermediate.
That's what a catalyst is.
Yeah,
Right back into.
right.
Right back.
That's one of the characteristics. Right. The other characteristic is it speeds up the reaction. This is a different mechanism than you would see without the catalyst. Without the catalyst, that would be what's happening. With the catalyst, you give it an alternate route, which is faster. Actually, I think this is the slow one and this is the fast one. Relative to one another. All right, let's see. Let's skip those. How about this one? 17. What is the order of the rate law with respect? Oh, based on the data up here. Okay, so this is going to take some work. All right, let's put do we need to put all that? We don't need to put all that data up here, do we? So what you do first is write the overall rate law with variables for the orders. So the rate then would be equal to K times the concentration of manganate minus to some order. And then the second one would be H2 oxalate, H2C2O4 to its power. And then the last one, hydrogen ions to the P. Okay, so all we're getting at for this one is what's the order of the rate law with respect to manganate? So we need to pick the two These are 1, 2, 3, 4 experiments, independent experiments. And we want to pick the one where these two remain constant and that one varies. So that would be, the first one would be a good choice, wouldn't it? Right, so the rate for the, let's do the second experiment first and ratio the second on top and the first one on the bottom. The reason for that is the faster rate is number 2, and divided by the lower rate would give us a whole number rather than a fraction. Okay, so what's the rate of the first one? It's 8 times 10 to the minus 4 divided by the first one, which is 2 times 10 to the minus 4, correct? Then we're going to ratio the law. And the value for manganate for the second one is 2 times 10 to the minus 3 to the n, and the first one is 1 times 10 to the minus 3 to the n. And the oxalate is 1 times 10 to the minus 3 for both of them. Let's see. That's m, excuse me. N. 1 times 10 to the minus 3 n. And then for the hydrogen ions is 1. B, P. These are going to cancel. These two are going to cancel. Oh, we left out K. K's are going to cancel. And we're left with 1 divided into 2, which is equal to 2. Right? 2 to the, not N, M. Yeah, I have to stick with it. I put M first, didn't I? There we go. And 2 divided into 8 is 4. So 2 to what power gives you 4?
2.
So it's second order with respect to the manganate. That's how you calculate it. All right, number 18. Static electricity.
Oh, shocked you.
Yeah. Okay, 18. The rate law for this reaction is NO squared O2. Okay, what happens to the rate when the concentration of O2 is tripled? If we say 3 times, if we go from a value to 3 times that value, what happens to the rate? Because it's to the first power. So it only goes up 3 times. So it's tripled. B, the rate triples. Let's see, actually this one's a duplicate. So we'll go down and hopefully find the other one. We'll stop at 24. Okay, 24. What fraction of a reactant remains after 5 half-lives of a first order reaction? Okay, so a first order reaction half-life is going to be, just a minute. What fraction of a reactant remains after 5 half-lives? You know what? It doesn't matter what the order is. When you say half-life, that means after one half-life, half of it's left. So that's blue smoke, that first order comment. Doesn't matter. Right, so if you start off with a certain amount, say you start off with 1. After one half-life, what you got left? A half of it, right? A half. And then if you go, let's see, that was the first half-life. The second half-life, you got a quarter of the original. The third half-life, you got an eighth.
Then 60,
The fourth half-life, you got a 16th, right?
32.
Right. There you go. So you got a 30-second left over. The other way that you can look at that is it's 1 divided by 2 to the 5th power. And 2 to the 5th power is 32. Okay. All right, 25 is based upon that information given just before 25. 2A, 2, A sub 2 plus B sub 2 yields C. And the following mechanism is proposed. The fast, step 1, is fast. And it's A squared plus B squared plus B squared yields R plus C. And step 2 is very slow. Very slow. And it's A sub 2 plus R. R is an intermediate, yields C. Okay. Oh, I wrote all that up there. The question is, which step is the rate determining step?
Oh. I
It's,
didn't get to.
it's the second one. It's the slow one. I thought we were going to have to derive a rate law from that, which we could. Right? We could write a rate law for this one. That's where you would start, with the very slow one, right? This would be, say, K1. Well, this would be more difficult because this is not given as a fast equilibrium. So let's not mess with that. I'll just get bogged down in details for that one. 26. For a reaction where we have yields products, and it doesn't matter what the products are actually. A0 is 6.4 molar. So at time t, 0, this is 6.4 molar. That's where we start. The first 2 half-lives are 60 and 30 minutes respectively. So after 60 minutes, how much A do we have left? 3.2 molar. Right, first half-life. Second half-life is 30 minutes.
1.7.
So we go 30 more minutes. And that means a total of 90 minutes.
1.7. 1.5 plus 2. Plus 1. Yeah, it'd be 60. It'd be 1.6. Yeah, 64, 32, 16.
Yeah.
1.6.
Half of that is 1.6. Yeah. Okay. Now, what's the question? If this reaction is known to be 0 order, calculate K.
What?
All right. If we know it's 0 order, all we need is half-life is A0 over 2K. Right? So if we know it's zero order, we could pick either one. Let's just pick the first one. So the first half-life is 60 minutes, and starting with concentration 6.4 molar
What?
divided by 2K. Solve for K. .4 divided by 120. So I get 5.3 times 10 to the minus 2. Oh, we got 3 significant figures. That's okay. That's the closest answer. Okay. 31.
Wait, don't erase that, 1 second.
Okay.
Okay. Oh, I'm good.
31, I think. 31. All right. Let's see. We have 2 rate experiments, and the K was determined at 2 different temperatures. Oh, this is an Arrhenius problem. So at temperature 30 degrees, at temperature 30 degrees C, the K turns out to be 1.38 times 10 to the minus 4. And at temperature equals 49 degrees, the K for that one is, let's say this is K1, this is 1 and 2, this is 1 and 2, is 1.21 times 10 to the minus 3. Okay. So what's the activation energy? Well, you have 2 ways you can solve this. One is you'd have to determine the slope of the line. You'd have to plot that data and determine the slope of the line. But we got another equation that works for that. It's a modified Arrhenius, and we're going to need temperatures in K. So 273 plus each one of these. So that's 303 K. This is 322 K. The equation I'm looking at is the natural log of these 2 Ks equals the activation energy divided by R times 1 over T1 minus 1 over T2. Right. This is the integrated equation for, this is one version of the integrated equation for the Arrhenius. So we've got the natural log of 1.38 times 10 to the minus 4 divided by 1.21 times 10 to the minus 3 equals activation energy. What's R? 8.3145. We use that version of the R. 1 over T1 is 303 minus 1 over T2, which is 322. There you go. Now, what's this value right here? This is 1.947 times 10 to the minus 4. And this is going to be divided by that value. Okay, so this has E sub A times 2.342 times 10 to the minus 5. This side we have that quotient 1.38 to the minus 4 and divided by 1.21 to the minus 3. And that one is 1.140 times 10 to the minus 1. And then we take the natural log of it. This is minus 2.171. So actually, I think there may be I think this needs a negative sign. Because if that's minus 1.140 natural log, yeah, that's going to be a minus here and a positive there. Activation energy can't be minus. So I think we left out a minus sign right here. So that would be, this is divided by minus 2.34 times 10 to the minus 5 equals E sub A, which I get 9.27 times 10 to the 4th joules. How many kilojoules is that? Because the answer is in kilojoules. Well, how many joules in a kilojoule?
10 to the negative 3.
10 to the positive 3.
That's what I said.
Joules in a kilojoule.
Oh, okay.
Yeah, 1,000. So if we extract 10 to the 3rd out of that value, like 10 to the 3rd times 10 to the 1st, 9.27, then this becomes kilojoules. This becomes 92.7 kilojoules. So I think there's an error in the review document. If you look at the back, yeah, there's a missing negative sign. You have a copy of that?
Of the work problems?
No, the review document itself.
Yeah.
Okay. There should be, if there's not one in yours, look on the right-hand side, the equation at the very bottom of the right-hand side. There should be a negative in front of this. That's missing. It's missing in my copy. I don't know if it's missing in your copy. See if it's there. Next to the last page, I think, or maybe the third to the last. Far right side, bottom equation.
Negative?
Okay, good. So it's only missing in my copy. That's good to know. You got that? We good here?
Yeah, I'm good.
Okay.
Thank you.
All right, it was 31. What time? 32. Consider the following balanced equation reaction and the experimental results that follow. What are the rate law orders for NO and H2? Okay, let's put this whole thing up here. I think it'll be instructive. 2NO plus 2H2 yields into gas. Let's see, these are all gases. And water. Okay, experiment 1. Number 2 and number 3. So the first one is 0.15, 0.015, 0.015, and then the third one is 0.030. And then the hydrogen concentration is 0.020, 0.040, and 0.020. And then the rates for the first one, 0.60, 1.20, and 2.40. Okay. We want to know the orders for each of these components in the rate law. So the rate is going to be K times NO. And I think I used to put N here first, I think. And then H2M. So we're going to ratio, we're going to find out the first one. So it changes from here to here, but it doesn't change there to there. So we're going to use 3 and 1. Number 3, number 1 for nitric oxide. So the rate's going to be 2.40 divided by 0.60 is equal to K, and then NO, which is in the third one, is 0.30 to the N power and 0.15 to the N power. And then H2 is the same for both of them, 0.02. Oops. That's 0.013, 0.015. This is M and this is. Okay. So this cancels, that cancels. And we got 0.6 into 2.4 is what? 4. Right? That's 4. And 0.015 into 0.03 is 2, right? So 2 to the N power, and N has to be equal to 2. So this value is 2. And the next one, right, these values are going to change. These values will change. And these values will change. Now we know that one's a 2 and that one's a 2, but we want to hold it constant. So these two would work best. This is going to be the first one and the second one, 1.20 and 0.60. And then this one is going to be 0.015 for both of them. And this one's going to be 0.04 and 0.02. Right, so this is 2, right? This cancels, cancels, and this is 2 to the M power, M equals 1. So that one is 1. So the orders are 2 and 1. C. Mm-hmm. Traveling on. Okay, 33. First order decomposition of H2O2 at minus 28 degrees C. That's pretty cold. Occurs with a half-life of 50 seconds, starting with a concentration of 25.2 molar. What will be the residual concentration of H2O2 after 5 minutes? All right. So we got a first order decomposition of H2O2. That means the rate equals K H2O2 to the first order. And the half-life expression for that is 0.693 divided by K. All right. What other information have we given? Well, we're given the temperature, but I don't think that's relevant. Half-life of 50 seconds. Notice that the half-life doesn't depend on the concentration. It's going to be a half-life no matter what concentration we start with. So this is equal to 50 seconds. So we can calculate K from that value. Right? So K is equal to 0.693 divided by 50. Or 1.386 times 10 to the minus 2. So the next thing we need is the formula for the first order reaction. The integrated law. So the integrated law, first order is natural log. The natural log of comes first. A will be H2O2 is equal to minus KT plus the natural log of H2O2 to the 0. The initial value. Okay, so do we have the information we need? Let's see. Starting concentration of 25.2 molar. So the starting concentration here is 25.2 molar. The K we just determined is equals minus 1.386 times 10 to the minus 2, and the time is 50 seconds. No, that was that time. The time they want to know is 5 minutes. So how many seconds? Since we determined the K in terms of seconds, how many seconds is 5 minutes? Huh? What's 5 times 60? Okay, I thought is that what you said?
Yeah.
Okay. 300. Let's see, I need to expand a little bit here. Plus natural log of 25.2, correct? And this is the answer we want right here. Okay. I need to make a little room. All right, so what can we do? We can do this one. Natural log of 25.2 is 3.2268, and 300 times that value. Let me flip that and change the sign. This is minus 4.158. So minus 4.158 plus 3.2268. And these two values together are negative 0.93116. And that's equal to the natural log of that concentration. So this concentration here, H2O2, is actually E to the minus 0.93116. Okay. So let's see. Where's my key? Here it is. I get this concentration now, H2O2, after 300 seconds is 0.39. Let's see. We started off with 394 molar. So the answer is C. We're good?
Good.
All right. $34.
How many are there on these?
I don't remember. Total. There are 43 questions and we're on 34. And I'm not picking every one of them. Okay. For the second order reaction, nitric oxide plus ozone yields NO2 plus O2. The rate constant has been measured to be 1.08 times 10 to the 7th at 298, and the activation energy has been measured to be 11.4 kilojoules over this temperature range. What's the rate constant at 233? Okay. So, that we need the same Arrhenius equation that we used before. We got two temperatures and we got two rate constants, and we want to know we got the activation energy. We want to know the new rate constant. Okay, so I think we need to extract the data from that word problem. It's getting kind of messy in there. So the rate constant, the first rate constant is equal to 1.08 times 10 to the 7th. At what temperature? Temperature is 298 K. Okay. The second rate constant is we don't know. Yeah. This is the unknown. But we are given its temperature, which is 304. We're also given the activation energy, which is 11.4 kilojoules. All right. So, and the equation that we're going to use is this modified Arrhenius. Natural log of K2 over K1. Oops. Wrong place. 2. Equals activation energy over R times 1 over T1 minus 1 over T2. All right. So if we look at the units of measure for this R, right, 8.3145 is joules per mole K. We got the temperature right. We don't have the energy term right. That's 10 to the third, right? 11.4 times 10 to the third joules, or 1.14 times 10 to the fourth joules. That's the term that has to go right in here in order to match this value there. Okay, so the natural log of K2, which we don't know, divided by K1, 1.08 times 10 to the 7th equals 1.14 times 10 to the 4th divided by 8.3145. And then the temperatures we do know. So the first temperature is 298 and the second is 304. Right? So let's calculate this number in here since there are no unknowns in that one. There are no variables in this one. 1.14 exponent to the 4th divided by 8.3145. And then let's take the reciprocal of 298. Let's see, there it is. And then the reciprocal of 304. And subtract this reciprocal from that reciprocal. And then multiply it times what I got for that one. And this should be 9.081 times 10 to the minus 2. Okay? So this is equal to this. How do we get that out of it? Well, remember your logarithms. The log of A divided by B is the same as log of A minus the log of B. So this would be the log of K2 minus the log of 1.08 times 10 to the 7th. Equals that value, 9.081 times 10 to the minus 2. So we can resolve this one. 1.08 exponent 7 and take the log of that, which is 1.6195 times 10 to the first power. And that's a negative on this side, be a positive on that side. So we're going to add that to this value. Now we have the natural log of K2 equals, let's see, I'm gonna give it to you in standard notation, 16.286. So now, in order to find out what K is, we need E to that power. Right? And K2, if I did correctly, is 1.18 times 10 to the 7th. Is that one of the answers? No.
I don't think so.
1.08 times 10 to the 7th. So let's see where I made a mistake. It should be 2.96, 10 to the 6th. Okay, let's see.
Difference.
Did I do this one right? 11.4 times 10 to the 3rd would be 11.4. 10.4. Yeah, that's right. Okay. So did I put hold on a second. One, yeah. Reciprocal of 1 minus reciprocal of 2. And K2 over K1. Yeah, that's right. Okay, so the formula's right. So we're going to have the log of K2 is at the higher temperature. Is that right? Activation is range 195. Rate constant at 233. So 2. Oops. That's it.
Yeah.
That's it. I got my temperatures. What's the rate constant at 233? All right, I used the wrong value. This needs to be 233. Okay, so here, the first one is right, correct? 298. Yes. So this is 233. All right. Let's see, this value is going to change. That value is going to change. Let's see, I'm going to divide this again. 1.14 exponent 4 and divide by 8.3145. And then I'm going to take the reciprocal of 298 and the reciprocal of 233, subtract those, and then multiply that times that value. This is, I did it right, minus 1.2835. And let's see. So we have minus 1.2835. And this is correct on this side. That's correct. So this is going to become positive on that side. So I just need to add this to that value. 1.6195 in the first power plus. All right. This value, not that one anymore. It's 14.91. Now I take that to the E power. 2.99 times 10 to the 6th. Close. 2.96. Yeah. Pick the best answer.
Mhm.
That just illustrates why we need to properly extract information from the word problem and put it in a form that fits the problem. So when I edit this, I need to just cut that snafu out, right?
What we found out.
Let's see what else we got down here. Oh. There we go. So let's see. I don't know if I can, maybe I can shrink it. Let me do that. There we go. How many? We got 3 that are dependent upon this one. So we can get the first one in there with a big graph. Which letter shows the activation energy without a catalyst? We go from reactants to products. We got to go up over the hump. So which one is without the catalyst? It's always the biggest hump. That's the red one. Yeah, it would be E. Yep, that's right. So E would be the activation energy for the uncatalyzed reaction. For the catalyzed reaction, you need the small hump, which is a distance of A. Yeah. And then the last one, which letter shows the activation energy for the reverse reaction without a catalyst? So we're going from this, we're going from products back to reactants.
It's dropping.
Yeah, going backwards like this. So it's from this level up to that level, which is C. Okay. That's how you read that graph. Now this one is time versus the natural log. So what order reaction is this?
What?
What order is this reaction? If we're plotting time against natural log?
No.
Huh? No, raw data is 0. Natural log is first order. You need some type of memory device to go from 0, 1 to 2. It goes from, let's see, what we say. We could say from none for no transformation of the data to the natural log to the reciprocal. Got to make something out of that. I don't know. You're better at that than I am.
First is called the natural.
Yeah.
Okay, I thought natural was its own thing.
Yeah, me too. We talked earlier.
Yeah.
No, natural log.
And then the
Where-
inverse is the second.
The natural log is base E. the LOG or the common log is base 10. Okay, so the question is, using that graph, what order is this reaction with respect to SO2, CL2? It's first order, B. What's the value of the rate constant, K? Well, what's the equation? Right, the equation should be the natural log of A equals negative KT plus the natural log of A0. Or substitute the actual value, SO2, CL2 here. So if we want to know the K value, we take the slope. And the slope of the line, in this case, is minus 2.20 times 10 to the minus 5. So you take away the negative sign, and that's your K, 2.20 times 10 to the minus. Yeah, B. Mm-hmm.
Those are, what are those things beside the A? That's a L and an E.
Where? Here? That's
Yeah,
square
beside-
brackets.
No, like the letters beside the A's. The L, is that an L? Or
Here?
an E? Yeah,
Yeah, the natural log, Yeah.
I guess,
LN.
you know.
Okay, I think that's it. Yep.